People ask me about how to prove that the moduli spaces are smooth. And also, so surely in yesterday's talk, the quotation about Bill Messing's theorem was done too briefly, so the assertion that it's an easy exercise after Bill Messing's thesis doesn't seem to be that easy. So let me do the exercise. So I'll do it in the case of the abelian variety. So here is an abelian variety over a field. So in the notation we have, this is always a perfect field of characteristic P. Okay. And I would like to show that this deformation, the deformation functor is smooth. So smoothness of the deformation functor, 0 over WK. Okay. So what's the key? So people also asked about representability. For representability, there is a set of sort of formal criteria that one need to check, and that are lab paths. You can just look at the Schlesinger criterions written in many places, and most of these are easy. The one that's more serious is to show that it is smooth. So what does that mean? So suppose that R0 is an Artinian local WK algebra. Okay. And then we have an abelian scheme A over R0 such that A tensor spec R0 to spec K is A0. Okay, so this is one. So we have one deformation. Okay. Now, so to show smoothness, it suffices to show the following situation. Suppose that R is an extension. It's a nilpotent extension. R. And we usually want to assume that it's square 0, but assume a little more, so that I times the maximal idea of R is 0. That also suffices, because you can devisage these nilpotent extensions in such a way. Okay. And I would like to show that, so must show that we can lift A over R0 to this nilpotent extension R. Okay. And that's one criterion of smoothness that we need to check. So now, what do we do? So by Grothendieck messing, so we know that we have this functor, which is D, just write A or A0. So let's say D or A0. Now, what I'll do is we'll observe that this extension, because it's square 0, therefore it has a trivial dp structure, as we explained yesterday. So making all just higher dp power to be 0. And we can evaluate that at R. So what do we get? So this is a free R module of rank 2G. G is always the dimension of A0 over K. Moreover, what else do we have? We know that, so D of A0, so this, if we evaluate it at R0, what that is nothing but tensoring over R with R0. So this is D A0 evaluated on R0. But now over R0, this is an abelian scheme. And therefore, it has a Hodge filtration. Because we know that this is a first homology, the ramp homology of A0 over R0. A over R0 in that notation. So it has a Hodge filtration, And so this is A over R0, over 0. And this is the Lie algebra of the dual abelian scheme over R dual. So that's the Hodge filtration. Each one, this is free, and then rank equals G. And this is also free of rank G. And what? Oh, first in the kernel. Oh yes, R0. I'm sorry. Thank you. So wrote it wrong. Okay. So this theorem, Grothendieck messing, what it says is that lifting this Hodge filtration to a direct summand over here is the same as lifting the abelian scheme. So now smoothness follows from the fact that this, let's call it S0 lifts to a direct summand. Namely, there exists some free R submodule of that free module of rank 2G, which is a direct summand. Okay. Moreover, so it's an easy exercise in algebra that lifting exists. So lifting both as Hodge filtration, and we know that it's the same as lifting the abelian scheme. And lifting, moreover, if we consider the set of all liftings, now just by looking at that diagram, we know that this has a natural structure as a torsor. It doesn't have a natural group structure, but if we have two liftings, we can compare them. This is sort of standard business about Grassmannian. Torsor 4. What's the torsor? The torsor is Lie of a R0 over R0. No deal anymore. Tensor over R0. Lie of A over R0. Tensor over R0. In fact, so this, yeah. And then R0 is over. And this, because R is killed by that, so I can really replace it over K over A over K. And this is over K now. So, and this is a vector space of dimension vector space. And that's why the tangent space of the deformation, so the dimension of the deformation functor.
Excuse me, I think it's rather the dual of the first tensor factor.
I'm sorry, there, I omitted the dual here.
No, I think it's the dual of the first tensor factor without the dual abelian variety. It's half of the quotient into the kernel.
Right, it's over there. I take the harm into that.
No, you take a hum from the quotient into the kernel to classify the different liftings.
Harm of the quotient. Now, if we have two of these, then take their difference. It's that for anything in the sub, I have two things above it, and then take the difference and project down. From the quotient to.
It doesn't matter.
Okay. Oh, but this okay. But this looks like. All right. So that's the exercise, And of course, I have done only one exercise. I also stated another exercise, which is that if you have a principal polarization, then the deformation functor is again smooth. The dimension of that is g times g plus 1 over 2. And for that, you need not only the effect that I stated, it's about lifting Hodge filtration, but you also need the behavior of the Dieudonné crystals under duality, which is also stated in the notes. Okay, so that's that. I'll get that out of the way. Now, what I would like to do today is largely utilitarian. In the sense, the first goal, there are two goals. One is that this will be introducing or reintroducing some linear algebra tools, which was mentioned in Bill Messing's talk yesterday. It's one of the Cartier, one of the Dieudonné series that was one of the many Dieudonné series that was mentioned in the last talk yesterday. And so although in one sense where it's already displayed, it's already explained, one doesn't seem to need to have that explained again. But it's always useful, at least for students. I remember when I was a graduate student, to have things explained several times. And also, the other reason is that I will need to sort of make things a little more explicit. And most of all, I would like to convince you that these things are doable. This is something you can compute by hand and reducing it to linear algebra. And also that this Dieudonné, this Cartier theory will be used in a very serious way in Francis' talk, I think next 3 talks. So before I do that, I'd like to do some examples. So I guess I'm trying to be a so-called user in the computer world. A user is supposed to be somebody who is not very intelligent, who only have looked at the manual and try to figure out how things work. And this is the mentality I'll be in for the first, maybe the next 10 minutes. So before I do the examples, so let me state what the ring I have in mind. So this is the part that I'll be recalling before doing the examples. So this is a ring. This is a non-commutative ring. So remember that K is a perfect field of characteristic P, so as before. And now there is this critical ring, of which we will build up linear algebra, which will decipher for us either Borsodi-Tay group or formal groups. Okay. It's written this way, but it's really not quite right. Okay. So what this is that you have structural equations. So commutation relations. Where for every A in omega, in the bit vectors, you have F and elements of the bit vectors. So commutes, almost commute up to sigma, where sigma is always the Teichmuller lift. Okay, so if you like, it's an automorphism of bit vectors which induces the Frobenius map on the residue field. If you realize this standard bit vectors as vectors with infinite entries, it's raising every entry to the power P. Okay. And now we have AV equals VA sigma for every element. Okay. And then FV equals VF equals P. So these are the structural equations. Okay. Now, if you like, you can also think about it as follows. You can think about it as elements in a formal power, in the finite sum, where I is in Z. So it's a finite sum, such that each AI is in an element in the fraction field of the bit vectors. So that's a local field in the general sense, such that for every I, the order of AI plus is bigger than or equal to the maximum of 0 and minus I. So all I'm doing is that I'm thinking about the way to decipher this is that F is P times V inverse. So that powers of V becomes negative powers of F becomes powers of V. Okay, so this is just this ring. Okay, so it's an easy ring in some sense. Now, so what we know is that so we have the black box. So I'll rephrase one of the black boxes, which sorry. Yes. AI is, now let me think. AI is, yes, yes. Yeah, I could have done this, if you like, because the powers of V becomes P times some negative power of V. Powers of F becomes some positive power of P times some negative power of V. So you're absolutely right. It's all here. Okay. Now, so the black boxes is that sort of modules, so left RK modules, which are free of finite rank over WK is equivalent. So if you like, I take this category, and there is an equivalence of categories between such things and p-divisible groups over K. So please, well, so we'll accept this as given. So K is a perfect field for of characteristic P. So now we're ready to do some examples. So well, we have some simple p-divisible groups. Okay. Perhaps the simplest one is mu p infinity. So this is the this is the limit of mu p to the i's. This is a Borsati-Tate group attached to the trivial torus. Okay. What does that correspond to? Well, it corresponds to this module, the underlying vector space, is nothing but the bit vectors. Okay. Now on the bit vectors, we all have seen that there is a sigma. Okay. So, and now, so what I want to say is that let me think, V and F, we need two operations. Now, so F is sigma, and while V is P sigma inverse. Okay. So here we go. So you have two operators. I'm just naming capital F to be sigma, and V is P times sigma inverse. Okay. And they obviously satisfy the commutation relations required for being a module over Rk. So in other words, to get a module required like this is that you have a free module of finite rank over the bit vectors, and have two operators, F and V. Now F is semi-linear in that way, and so sigma semilinear, and V is sigma inverse semilinear. So we have this, so that's one. So example one. Example two, now you may wonder, what would the constant Barsati-Tate group correspond under this situation? Well, but there is another one like this, which sort of, here I have the P and F that way. But what would happen if I just make a shift of this P from the position here to the position, so one notch down? So V is sigma inverse, and F is P sigma. Still, that clearly satisfies the commutation relations, and that is this. Now three, so let me make a module whose underlying module structure is free of rank 2 over, okay? So I have two bases labeled as E1 and E2. Now, if I want to have F and V this way, it suffices to say what effect it has on E and E1 and E2. That was specified. So I'll define F and V. I'll have defined two operators, and F sends E1 to E2, and then extend, and then F sends E2 to P times E1, and then extend by semilinearity. That's one such. And V is similar, although they are not the same operator, but on the basis they just look like this, they look the same. So we will get another. So this is clearly, so you can check that this clearly satisfies all these properties. So it corresponds to sort of left modules over this. Oh, I should say also, under this correspondence, the rank over WK corresponds to the height of the underlying Barsati-Tate. Okay, so I'll be adding a little more from time to time. So if you believe this, this will correspond to a height 2 Barsati-Tate group. The question is, what is it? Well, maybe here, I guess I'll follow the notation. In the nodes where a little k always denote an algebraically closed field. So I'll do that. So nothing really changed. And the answer, so if you want to identify this, you have all heard about supersingular elliptic curves. So the M corresponds to, this M corresponds to a supersingular elliptic curve. It's taking, so it's supersingular. You take a supersingular elliptic curve over characteristic P. Now you take its attached P divisible group and the resulting sort of module is just this. Okay. 4. Now next, I would like to introduce a series of examples. And to do this systematically, I'll take two integers, m and n, such that your GCD is 1. M and n are both non-zero. Okay. There are lots of such. And I'll define a P-divisible group, M sub MA, so over K, let's say. So the K is an algebraically closed field of characteristic P. Okay. And I define it by saying that its Barsati-Tate, or this, its Dieudonné module has the following form. So I'll write it's RK divided by one equation and let me look at this secretly, and I'm correct. Okay. So now it's time to tell you something more about this correspondence. Okay. So under this correspondence, so on the one hand, if you have a Barsati-Tay group, it has something called a dimension. And so dimension, if you have, so X, I guess that's notation, it's a Barsati-Tay group over K, and it corresponds to a Dieudonné module M. If that happens, we have already seen that the rank of M over the bit vector is exactly equal to the height of this Barsati-Tay group. Right? Now, there's another invariant, which is the dimension of X. If X is attached to a genuine group, a smooth group, you can, so if the, for instance, in the Abelian variety, then that group itself has a dimension. The notion of the dimension will then coincide. And what does it correspond here? This corresponds to, you take M divided by Vm. Now, since P is V times something, once you kill V, P becomes 0. Okay. So this becomes a vector space over K, and that we can talk about. It's finitely generated, and this is the correspondence. I should also say, as mentioned in Bill Messing's talk yesterday, that V corresponds to Frobenius on X. This is an unfortunate, so I'm hiding it so far. So for those of you who had some experience, there are many versions of Dieudonné theory. And especially there are some covariant and there are some contravariant. So for those of you who have seen these, so far I've been using the covariant theory. And in covariant theory, V corresponds to the geometric Frobenius, right? So it's not that F corresponds to Frobenius. It's different. It's exactly the opposite. Okay, now let's go back to here. So this is just a simple module defined by one equation. You can check that the underlying WK module structure is free. What's the rank of it? Or height? If you look at this equation, you can see that you have V, sort of higher powers of V or higher powers of F, they got killed away. And so you have powers of V and powers of F up until, both up to 1 less. And then you have, so you do a little bit of that, you convince yourself very easily that the height is nothing but n plus n. So I'll leave that to you as an exercise. Okay. Now, let's think about its dimension. What's its dimension? Well, the dimension is you kill all V. You model out V by it. But once you kill both V and this equation, you have killed also F to the M. So then you can see that the dimension of this, so you have killed out all F to the M. So you get a set of bases corresponding to powers of F from 0 to n minus 1. So the dimension of this is the dimension of K of M modulo Vm always. And in this case, it's just M. Okay? Now, another thing we would like to understand is, we would like to understand the asymptotic divisibility properties of powers of these operators F and V. Okay. So if you raise V, you iterate V many times, we would like to know how divisible that is by P. Okay. Now, if you look at this, equation, so how did I know I got it right? Because I secretly did some little computation. Right? So here's not a secret, is this. So you look at this equation. I multiply that, multiply this equation by v to the m. Okay? So this has one generator E. This generator is killed by v to the m minus f. Now if I raise to the power p, so if I call this generator E, then I see that v to the m plus n times this generator, is nothing but p to the n E. Right? I'm just multiplying both sides by v to the m. So you can see very quickly from this that asymptotically, if you take a high power v, then v behave in terms of divisibility, v almost look like p to the power m over m plus n. So in terms of divisibility, v is like multiplying by p to this fractional power. And this power is n, so you can check because this is a monogenic. Then asymptotically, so if you look at high power p, hit it on here, then it's divisible by almost that power divided, that power multiplied by m over m plus n. Okay. So a definition. So slope of this n is equal to m over p. The idea, of course, is that asymptotically, Frobenius is divisible by just p to the power m over m plus n. Okay. So that's a series of examples. And of course, you can see that there are special cases. If m and n are both equal to 1, what do we recover? We recover exactly example 3. Well, if one of the n and m is 0, well, the other must be 1 then we recover examples 1 and 2. Yeah. GCD is 1. Well, it's not used, but if GCD is not 1, this is a definition, just because I want to use it later. And the later here is right here. So because now it's easier for me to state, so there's a theorem, Dieudonné, Manin. Sorry. So what it says is that every Barsati-Tate group, or every p-divisible group, is isogenous, so over an algebraically closed field, is isogenous to some powers of GMN, so I. So it's a product of these. So in other words, if we don't care about the exact isomorphism classes, but only up to isogenous, then every Barsati-Tate group over algebraically closed field is isogenous to a finite number of products of the examples that we just did before. Okay. Moreover, these multiplicities are unique. So E, I should say, E, label it with E sub mn, and that's uniquely defined. So this is the theorem. And now we can define complete what Franz did yesterday. So we can define the Newton polygon. This is one of, sorry? The GCD condition, yes. I mean, otherwise, if I don't want them to be, there are problems. But so here's MN, But this is summing over all pairs satisfying the above condition. Okay. So now it's the definition of Newton polygon for X. So what do? We saw that combinatorially, to define the Newton polygon, it suffices to define a sequence of slopes with multiplicity. Right? And so what's the sequence and what's the multiplicity? If X is like this, it's that we have M over M plus N's, and then has multiplicity the multiplicity is E times M, this multiplicity of this, how many times? But each time it appears, we want to repeat the slope as many times as its height. And that defines the Newton polygon. And also, I should warn you, if you have sort of begin to get into sort of reading these materials, there are in the literature, so there are slopes defined by using V and F. So here I'm sort of using the slope defined by V, because that corresponds to Frobenius. But if you use F instead, then it becomes not using M over M plus N, but rather N over M plus N. So one always have to be careful. But for abelian varieties, you have no such problem, because for abelian varieties, there is a duality statement, and therefore you can always choose a polarization. And therefore, abelian varieties, whenever you have one appearing, the other must appear. So if slope lambda appears, the slope 1 minus lambda must appear, and they have the same multiplicity. So, and the Newton polygon is symmetric, and you just don't get confused. But if you have to think about a non-symmetric situation, be careful of what was being sort of said. Okay, so I guess I've spent a lot of time just playing with the linear algebra. Now, the next thing is I would like to show you. So, I don't think I have enough time to do all the story. But and also, the story in itself has been presented in yesterday's talk. So I'll try to see. Maybe I should do this. So in some sense, I'll be, before that, I think there's a good exercise here. So it's an exercise is to show that the set of all Newton polygons, or the set of symmetric Newton polygons, Franz explained yesterday that there is a partial ordering on the set of Newton polygons, and also therefore also on the set of symmetric Newton polygons. Okay. Now, so if you forget about everything else that been coming from p-divisible groups, but just remember the combinatorial structure, that it's a partially ordered set. So we have this partially ordered set. Now, one thing, one property about partially ordered set is that sometimes these partial orderings can be very wild. But the exercise is that they are ranked. Ranked partially ordered sets. Ranked meaning that in a partially ordered set, if you take two of them, suppose they are comparable. So there's a chain from one to the other. Okay. And then you can think about maximal chains. Okay. Now, the rank means that if you fix two endpoints, then any two maximal chains have the same length. Okay. So this is an amusing exercise. So anyone can do. You don't need to know anything about formal groups and anything. And this, in fact, has some geometric implications in things that Franz, I think, probably will mention. Okay, now. So I'll tell the story, but about Cartier, about the Cartier theory. So this is one of the possible Dieudonné theory. So among other things, so the features is that it's covariant, that I've said. But one thing that's really important, and this is one of the few situations that I know of in algebraic geometry, is that you can use these to construct non-infinitesimal deformations. Real deformations, so can be used to construct deformations over rings like K double bracket T. So this is a standard thing. In usual deformation theory, each time you have to worry about obstruction, and even if you know it's smooth, you don't know how to write down a family. But this is one of the rare situations that I know I can't think about many other situations that can just really write down a family over a formal curve, the spectrum of a formal curve. So it really goes out. And this feature will be used in Francis' talk. Okay. So what is Cartier's theory? Cartier's theory has the advantage of being completely elementary. In the following sense, that if you work with it for, I'll say, be conservative, you invest a week doing nothing but playing with the linear algebra, and that you will get a pretty good hand of it. There's not much theory going on other than familiarity, and familiarity brews content. So, okay, so what's the theory? So there is a key observation. But this is the underlying phenomenon for everything that follows, is that there is a formal group. It's an infinite dimensional formal group of which you can build every formal group, commutative smooth formal group out of it. So in some sense, it's that if you think about the category of all smooth formal groups, in some sense, it looks like it has a free generator in the sense of abelian abelian categories. Although, of course, we know that the category of commutative smooth formal group is not abelian. But this thing that I'm going to describe makes it look rather seem like a free generator. And so I'll use the notation lambda, and I guess since the way the note is written, so there is an exception. For a while, although so far I've been trying to be consistent, whenever I write a little k, it's an algebraically closed field of characteristic P. Now, temporarily, for today only, K is an arbitrary ring, commutative ring with identity. Now, so it goes to the set of the category of all abelian groups. So what is it? If you take a nilpotent algebra, it gives you the set of all elements of the form ai t to the I, where, so this is a finite sum. This is an important point. And t is a formal variable. And these ai are in there. Okay. What's this? This you think of as a subgroup of, let me write, K direct sum with n. So that's a commutative ring with identity. And then a joint T. It's a polynomial ring. Generally, a polynomial ring you may think it doesn't have a lot of units, but in this case, because you have lots of nilpotents, it does. So in other words, we are using the GM, the standard, the trivial torus, and use that, and we look, and then sort of spread it out by adding a formal variable to get an infinite dimensional formal group. And this is smooth, as you can check easily. And what is it? This is that this is a restricted version of the universal Witt vector, the ring of, or the group of universal Witt vectors. So this is that. Now, I have 10 minutes or so, so I'll try to be quick. Now, so one can choose, so having this, now if you have a group, have a smooth formal group, as defined yesterday in Bill Messing's talk, that is, it's a functor from here to here, which is exact and smooth. Okay? And now, so there's a Unida type theorem which says the following. If you look at homomorphisms from lambda to a given group, so if you have such a homomorphism. But on the other hand, so you have this homomorphism. Now, in here, you have, so to speak, a universal element by evaluating it, by evaluating n, so n, this is here, the functor is given, but we evaluate n as, so to speak, k times k double bracket x. So so I mean, in here, although it's nilpotent, you can pass to inverse limit, so you can also feed in topologically nilpotent algebras. Okay. Now this is obviously a topologically nilpotent algebra. Okay. So I feed that into it, so I have a homomorphism of lambda evaluated at this nilpotent ring, topologically nilpotent ring, and I have something here. Okay. So I evaluate, and here, this is a special element in lambda of this topologically nilpotent ring. That's a special element. And therefore, having a homomorphism, it gives an element here, right? And this you can think of as having formal curves. This is formal curves by definition. In G, where x is the variable for the formal curve. Okay. So we have this, and the statement is that this is an equivalence. This is a bijection. So when we talk about formal curves, it's nothing but, so you can think about a formal curve as a homomorphism. Okay. Now having that, then it's very good. So if you believe in this business, that lambda is a formal generator, then the standard formalism for a Beaton category is that if you know some element, you just have to get an element. It's equivalent to knowing hum of this free generator into that given element. This is an abstract form of the Morita equivalence. So if you believe in all these, then what we get is we can look at the notes for specific statement. But it roughly says that so the modules over, now I would like to say endomorphism. So if you look at this, it looks like a module over the endomorphism ring of lambda, except that it will be a right module. So and it's a convention that started a long time ago. Nobody is going to change that. So we'll be using left modules. To use left modules, therefore, we will not use the endomorphism algebra, but rather it's the opposite algebra over that. So that's what we think about. So this as just not forgetting about that's a group. It's a hum of lambda to this group, but rather thinking about it as a left module over this. Okay, that's plus some filtration. The filtration, it's written in the notes. You can read. So there are certain mild conditions that such thing needs to be satisfied. And then the theorem says that if you have any module, left module, over this ring, then satisfying those mild conditions that I stated, then you get a smooth formal group. It's an equivalence of categories. And moreover, it's also written in the notes, that you can recover the group from this module. If you believe in this, you can almost do it. If you have a module N, it's a left module, so this will be called the Cartier ring over K. It's a big ring. And to recover that, the endomorphism, the group itself is a left module over its endomorphism algebra tautologically. And therefore, it's a right module over the opposite ring. Now, it almost like you take the tensor product, you recover it. And in general, you have to do a reduced tensor product because there may be certain junk relation that you have to kill because of the topological relations. And that's that. This is very simple. And I guess the key really is that, so in some sense, it's not a surprise. You have something almost like an abelian category. There's a general theorem that if you have an abelian category, you can decipher with satisfying some mild conditions, such as for having some free generators. You can decipher that as sort of a subcategory of modules over some rings. Okay. So the serious business is to understand this ring. If M is that group. So in some sense, I'm giving the reverse. So there's an equivalence of category. So one is taking a group, and you make that construction. And the other is taking some sort of tensor product. Okay. Now, the key of this is to understand the ring structure of this. So the ring structure is written down in the notes. I'm not going to repeat it, so just copying it will take a lot of time, and I didn't prepare my slides. And in this situation, I happen not to think the slides wouldn't help very much. The key is to play with them. So I strongly advise anybody who wants to get your hands on to play with it. If I have time, I'll do one more example after that. But I need some time to go a little bit further because this ring is too big in general. And this is not what people usually use, precisely because this ring is a little too big. Okay. So the point is that, so suppose that the base ring, K, is Z localized at P algebra, meaning that every prime other than P is invertible. But suppose that's the case, then the theory simplifies in the sense that this ring gets a lot smaller. Okay. Now, so what's the point? The point is that one can write down very explicitly, but in order for any formula to make sense, you really need to get used to these relations in the ring. So it's written in the notes. Okay. So you have an idempotent in this ring. Now, then what happens is that you can use this idempotent. You can use this idempotent to cut down a much smaller ring. Okay. And similarly, if you have a Cartier module, so I write this as MP, M of G. If I have a Cartier module, M of G, then I define a much smaller one by taking the Cartier module of G over the big ring, and then just multiply it by epsilon P. Okay. So this, it's obvious that this MP of G is a module over the Cartier P ring, right? And the fact is, maybe sort of surprising when you first see it, but after a while, it's not a surprise anymore, that you lose no information whatsoever. So in this situation, we have, so again, commutative smooth formal groups corresponds to left modules over the Cartier P rings plus some mild condition, topological condition. Again, the condition is written in the notes. Now I think I have maybe 5 minutes left. First, I would like to explain the relation between this ring and RK that we introduced at the beginning. What's the relation? They're not the same. So you can read the notes and see. So again, the point is that there is a very precise description of elements of this ring by generators and relations. We know what the elements are. We know how to manipulate them. But so I'll revert to the situation we have. So what we have, RK here, is that this is a completion of that. So a completion. And you may ask, so how do you do the completion? And here is an answer. If you remember this notion of summation AI VI, Z satisfying that order of AI bigger than or equal to the maximum of 0 and negative I. You have this, and then, so you want to complete such things, and we'll complete it with respect to certain topology. And the way that the topology goes can be described as follows. It's the same as requiring that the order of AI, so this is the order P normalized p-adically, plus AI goes to infinity. So it's nothing but this. So what's the result? The result is that this being a bigger ring, it has less modules in some sense. Because for a module over RK, to be a module over this completed ring, it's that certain limit condition should satisfy. Certain limit should go to 0. Okay. If it happens, it becomes, you pass to completion, you get a module over this Cartier ring. Okay. But it's not satisfied, you don't. Okay. For instance, you can see some examples. For instance, this constant group.
So this goes to infinity as I goes to infinity.
As I goes to infinity. The absolute value of I goes down. This is elementary. So we have that. Finally, I think I have about 1 or 2 minutes left. Finally, can't find the sponge for some reason. Oh, I'm blind. Sure.
This ring,
Yes.
if I would write W double brackets V and then single brackets F, is that exactly this ring?
Yes.
Okay.
No.
Oh,
I mean, you can have infinite powers of F, infinitely many non-zero powers of F.
well, I think it depends. So this Cartier ring, another description is the standard so V to the M, let's say A M N, V and for every, so A sub M N in K for every M N, and then for every M, there exists a constant such that A sub M N equals 0 for all M bigger than or equal to C sub M. That's that.
I mean, that's certainly correct.
Like the first digit is single bracket.
Yeah, I'm not sure, so take double and single bracket. But this ring, if you decipher it, it becomes the ring of convergent power series that unfortunately seems to have erased.
I mean, if you want the bit vectors embed in this ring via
The bit vector is that you have A, the bit vector is A, and then embeds go to A equals A0, A1, and so on. And that gives V I, A sub I, F to the power I. So I bigger than, and that's an embedding of the ring of bit vectors, p-adic bit vectors, into here. So the meaning of these is written in the notes. So, but I would like to mention one thing, if I can just take a few, maybe 2 minutes more. Right, let me write down something. So the point I was trying to make, which will be used in Francis' lecture, is that using the Cartier theory has the advantage that you can write down really families, not only just over Artinian rings, but over quite non-Artinian rings. So here I'll write down one such family. Okay. So I take the Cartier ring, but I use a base ring, or K, let's say K is an algebraically closed field. Now, I'm reverting to the previous notation, characteristic P. I have a formal power series ring, a number of variables, and now I divide out by one relation. And what's that relation? I take x0 plus x1 times v, and similarly to x sub h, I'm sorry, this is h minus 1, this is correct. V to the power.
So the power series ring is in x0 through xh.
Oh, so, I'm sorry, not 0. This is 1. So this is what I meant. H minus 1 plus v to the h minus f. That's the relation. Okay? What this is that this is, so if you think, if I reduce modulo the maximal ideal here, namely I kill off all the xi's, then I get one relation, namely v to the, oh, I'm sorry, this is v to minus 2. Okay. V to the h minus 1 equals v. Okay. What that is, if you remember, so this is one of the examples we had. This is a one-dimensional formal group of height h. Okay. And what, this I can, in fact, oh yes, this is correct. So if you like, one can use this. One can, in fact, also use the bit vectors, if you like. That's because the bit vectors, this is also with sort of a Z parenthesis P algebra. Okay. So we have this. What this is that we have written, this happens to be a very, very explicit form of the universal deformation space of that one-dimensional formal group of height h, or one-dimensional Barsati-Tate group of height h. And this is not for idle, so it's not something that we just invented. This actually happens as the formal completion at a point of certain moduli varieties. Okay. And so so this is something very explicit you can construct. In some sense, we seem to understand it. Okay. On the other hand, if you remember, being a deformation space, we have the automorphism group of G1, H-1 operating on it. So my both assertion and exercise is that the assertion is that this is an interesting action, and that this is something it's possible to compute by hand. And it's interesting, I think. And so for people who want to sort of really understand how things work, this is a good starting place to play. Thank you.